When we did amortized analysis on the operation to decrease the minimum key value node, we assumed that the maximum degree of any node in a Fibonacci heap can be upper bounded by log n. And by this assumption, we proved that the amortized cost of deleting the minimum key node is log n. And the same is used in obtaining the amortized cost of the delete operation as well. The agenda for the next two lectures, L20 and 21, is to prove this upper bound. So we shall try to see what is the maximum degree of a node in a Fibonacci heap. We need to prove that the upper bound is log n. Why we are interested in obtaining an upper bound on the highest degree of a node in a Fibonacci heap? This is the reason. We have obtained the amortized cost of the operations Fibonacci heap extract min and Fibonacci heap delete as order of the maximum degree. This is the notation for maximum degree. We need to prove that the maximum degree is upper bounded by log n. And before we prove the main result, let us see what this lemma is claiming. Let x be a node in a Fibonacci heap with the degree x dot degree. That means we are looking at a node x whose degree is this value, and suppose this is k, and then k is the degree, means there are k child nodes, and let y1, y2, etc. yk be the children of x, such that for all I from 2 to k, yi, for example y2, is added as a child of x only after adding y1. So we are assuming that the children y1, y2, etc. yk of a node x is added as children of x in that order, first y1, then y2, likewise. And if these child nodes are added in that order, we will prove that y1 dot degree, that is the child which is added first to the node x, is having degree greater than or equal to 0, and for all other nodes yi from 2 to k, yi dot degree is greater than or equal to I minus 2, which is a non-trivial statement. We need to have a proof. So we are looking at a node x which is having k child nodes which are added as child nodes in this order. After x is getting the first child y1, and after y1 x is getting y2 as the next child, then it is getting y3, etc., and finally yk. So we are considering a situation where x is a node in a Fibonacci heap which is having k child nodes, and we assumed that the child nodes are added in this order, y1, then y2, likewise till yk. And not that in a Fibonacci heap, how are you adding a child nodes and when is it happening? If you recall, when you want to insert a node, we so that the insert procedure inserts the new node as a single node tree to the root list. That is how you add it. But when a node becomes a child for other is only in the consolidate procedure that we do as a part of the delete minimum key node procedure, okay, or extract min, and I hope you remember those. And it is very easy to see the first result, because for any node the degree must be greater than or equal to 0, which is the number of children. So that is a trivial result, nothing to prove. And this is what I was trying to tell. Recall that the operation to insert a node x to a Fibonacci heap inserts x as single node tree, as a single node tree to the root list. So this is what we, so given a heap instance and a node, we will put the node 21 as a single node tree here. So that is what we did. So node 21 is getting as a single node tree in the root list. Also, a node y is added as a child of another node x, say like this, by the operation consolidate. If you recall all the operations that we discussed over the Fibonacci heap, this is the only procedure which is setting one node, say y, as a child of another node. And if you recall what is this procedure, when we found that there are two trees of the same degree, then we will make one tree rooted at say 17 a child of another tree with the same degree. That is what we did. So here we found that already the array is pointing to a tree with a degree 1, and you are now getting another tree with degree 1, but at most one tree is allowed. So you will now make one tree, which is this one, the child of the other. This is what we did. Previously 23 was the only child of 7, and now because you have already a tree of degree 1 pointed to by index 1, and you are now processing another tree with the degree 1, you have to combine them into a single tree. Note that whenever you add a child node like 17 here to a node x, already you have both these trees with the same degree, or the number of child nodes for x is same as the number of child nodes for the 17, which is going to be added as a child. So this is what I was trying to tell. The operation consolidate adds a node y with some degree. You take that degree as I in the previous example 1 to the other node x with the same degree. This is what we know. Only when both the nodes are having the same degree, you are setting one as the child of other. Okay, so you are combining two trees with the degree I each, and one becomes a child of the other. So the degree of the root node will be increased by 1. Previously it was I plus 1. Copy that argument to here, exactly the same argument. That is, yi is added as a child of x only after adding the first I minus 1 children of x, because if you are adding I as the y as the ith child, maybe ith child is going to be y, then why is it done? Because you are having two trees rooted at x and y, both having the same degree, then only the consolidate procedure will add y as a child of x. So already you have I minus 1 child nodes for x and I minus 1 child nodes for y. Okay. Then you will add that yi as the ith child of x. Then it is very clear that already you have I minus 1 childs, y1, y2, etc., yi minus 1. I hope you are getting, otherwise please watch it again. So naturally, because you are going to add the ith child, the degree of x must be greater than or equal to I minus 1. Now because you are adding y as a child of x, both y I and x must have the same degree. So the degree of yi must be greater than or equal to I minus 1, because when you add yi as a child of x, both x and yi must have the same number of children, which is I minus 1. Okay. Now note that in the Fibonacci heap, in a later stage, maybe yi can lose a child. See, when you did that decrease key procedure, you are cutting a child and taking it as a tree in the root list, right? So later on, this node might have lost a child, and not recall that it cannot lose more than one child. The moment it loses the second child, that tree will again be removed and taken into the root list as a fresh tree. I hope you remember that from the previous lecture. So it must be greater than or equal to I minus 1 originally, but later on it may lose a child and hence the degree must be greater than or equal to I minus 2. Originally it was greater than or equal to I minus 1, but later on it may lose a child, and so you can always say that it is greater than or equal to I minus 2. So that is the result that we wanted to prove. Okay. I hope you followed the proof, otherwise please watch it again. For the interest of time, let me proceed. Maybe now and in the next lecture we will see why the heap is given the name Fibonacci heap. First look at Fibonacci sequence. I hope all of you know the Fibonacci sequence. It goes like this. The first Fibonacci number is f0 is 0, then f1, f2, likewise it goes. The kth Fibonacci number, when k is equal to 0, it is 0. When k is equal to 1, it is 1. Directly defined cases. For all values of k greater than or equal to 2, Fibonacci at k, Fibonacci value at kth index is defined as fk minus 1 plus fk minus 2. This is the definition of Fibonacci sequence. Now we are going to have a lemma on the Fibonacci sequence. We are claiming that for all natural numbers k including 0, the k plus 2th Fibonacci number can be written as 1 plus the sum of the Fibonacci number till k, that is f0 plus f1 plus etc. plus fk. If you look at that sum, then what you are getting is fk plus 2. So this is a result that we can prove using the principle of mathematical induction on k. Base case, when k equal to 0. I hope you remember the Fibonacci sequence. We want to prove that when k equal to 0, it is 1 plus this summation. The value of k is 0. So for I is equal to 0, sigma fi. f0 is 0, that you know. So the result is 1 plus 0, which is 1, which we know that it is f2. f2 is 1. That is what we know about the Fibonacci sequence. So the base case is done. Now the hypothesis, you assume that it is true for this value, that is fk plus 1 is equal to 1 plus summation I is equal to 0 to k minus 1 fi. So, this is the assumption, which is the hypothesis. Now, try to prove the statement for k is equal to, or here you want to have k plus 2, or here you want to have k. From the definition of the Fibonacci sequence, we know that fk plus 2 is nothing but fk plus 1. Now, from the hypothesis, you can substitute the value of fk plus 1 here. So, it becomes this quantity. Just verify that it is this quantity. Now, you can say that if you take this fk inside, you can write it as 1 plus summation I is equal to 0 to k. So, you are taking this fk also inside fi, and this is exactly what we wanted to prove. F at k plus 2 is nothing but 1 plus summation I equal to 0 to k fi. So, that is the lemma. So, today we have proved 2 lemmas, and in the next class we shall make use of these lemmas to prove that the maximum degree of a node in a Fibonacci heap can be upper bounded by log n, where n is the number of nodes in the heap. Thank you.